Hi everybody, this is Blake Pilcher and I'm here on Trouble Math 44, and today we are going to talk about Binet's formula. Now Binet's formula is an explicit formula for the Fibonacci sequence. So first of all, before we go into this, let's just review what the Fibonacci sequence is in the first place. So the Fibonacci sequence is this sequence of numbers: 0, 1, 1, 2, 3, 5. Can you see the pattern yet? 8, 13, 21. Do you see the pattern? 34, 55, 89, 144, and it keeps on going. Does anyone have any guesses as to what the pattern is? Pause the video for a second and think about it. Okay, so did you guess the pattern? The pattern is actually you add two terms of the sequence and you get the third one. So 0 plus 1 is 1, or 1 plus 2 is 3, or 2 plus 3 is 5, or 3 plus 5 is 8. That's the pattern. Now, how do we write out this pattern in more mathematically formal terms? Well, here's how we do it. We'd say that the nth term, f sub n, is equal to the n minus first term, f sub n minus 1, plus the n minus second term, f sub n minus 2. Right? So what this is saying is no matter where we are in the sequence, we're going to add the two terms before to get the new number in the sequence. That's all this is really saying. And we need to have some initial conditions here. So we're going to have that the 0th term is 0, so f sub 0 is 0, and the first term is 1. Now we need to have that because we need two terms to start with, right? If we didn't have that, we'd have to try to find them by finding the negative first and the negative second term. And that doesn't even make sense, right? To try to find f sub 0 equals f sub negative 1, or the negative first term, plus f sub negative 2, or the negative second term. That doesn't even make sense, right? So we need to have these two terms here to start out with so that this formula does make sense. This formula is all fine and dandy for if we're trying to figure out a new term in the sequence when we have the two terms before. But here's the problem though. What if I was trying to find the 40th term in the sequence? Well, I need the two terms before it to add up. So I need the 39th term, f sub 39, plus the 38th term, f sub 38. Well, here's the thing. How do I find the 39th term? Well, I need the two terms before it. So the 38th term plus the 37th term. Well, how do we find the 38th term and the 37th term? Well, the 38th term, you need the 37th and the 36th. Then the 37th, you need the 36th and the 35th. Do you see the problem here? The problem is that in order to figure out this 40th term, I got to figure out all these terms before it. So I need to know 39 of these terms before it to figure out the 40th term, right? And this is really, really impractical, especially when we get to really, really big terms in the sequence, right? So how are we supposed to find the 100th term? We got to go back and do all 99 of the terms before? No, thank you, right? So we need to find an explicit formula here so that we don't have to do that. So this is actually called a homogeneous linear recurrence relation. Now, how do we solve homogeneous linear recurrence relations? In other words, how do we figure out an explicit formula from the homogeneous linear recurrence relations? Well, this is actually how you do it. What you're going to do is you're going to take this formula over here, and you're going to make it into a polynomial equation. The latest term is going to be the highest degree term in your new equation. So we'll make f sub n, we'll make that x squared. And we'll make f sub n minus 1, that term is right before f sub n, so we need to make it a degree lower, right? X squared is a second degree term. X to the first, or just x, is a linear term or a first degree term. And then f sub n minus 2, we need to make that a 0th degree term or a constant. So we need to do x squared equals x plus 1. This is called the characteristic equation. So the next thing we need to do, now that we have this characteristic equation, is we need to solve this characteristic equation. So that's what we're going to do. We will solve the equation x squared equals x plus 1. Now this is a quadratic equation, so I'm going to have to move everything to one side and have the other side be 0. So if I subtract x and subtract 1, I get x squared minus x minus 1 equals 0. Now we can't factor this, so we've got to use the quadratic formula. So we'll say a equals 1, b equals -1, and c equals -1. And then the quadratic formula is negative b plus or minus the square root b squared minus 4ac all over 2a. Our teacher used to sing this in a song. Now, let's actually plug in some of these. So we're going to plug in -1 for b, so negative 1 plus or minus square root. We'll plug in -1 for b again, so we get -1 squared minus 4 times a is -1, so we'll plug in -1, times c, which is -1. Oh, I'm sorry, a should be 1, not -1. And then that is all over 2 times a, which is 1. So now what we got to do is we got to simplify what we have. So let's do that. So -1 is +1, plus or minus the square root of, well, -1 squared is -1 times -1. Negative times a negative turns into a positive, so it's just +1 plus, this is going to be a plus because we are multiplying two negatives together. So 4 times 1 times 1, that's going to be plus 4. And then all that over 2 times 1, which is just 2. All we have left is we got to add up everything inside the square root, and we get 1 plus or minus square root of 5 all over 2. So in other words, x equals 1 plus square root of 5 over 2, or x is 1 minus square root of 5 over 2. What do we notice? Well, we notice that this 1 plus square root of 5 is actually the golden ratio. We're going to say that's equal to phi, right? Phi is the golden ratio. And then 1 minus square root of 5 over 2, it actually can be shown that this is equal to 1 minus the golden ratio, or 1 minus phi. So here are our solutions. X equals phi, or x equals 1 minus phi. Phi being the golden ratio. It can be shown now that we've solved this characteristic equation, the explicit formula for the sequence is equal to some kind of constant, we'll just call it C1, times phi to the nth power. Phi is the first solution to our characteristic equation, plus C2, a second constant, times 1 minus phi, quantity 1 minus phi to the nth power. And 1 minus phi is the second solution to the equation. It can be shown that this in fact works for some constants C1 and C2. Now the only thing is we don't know what those constants are yet. So how do we figure those out? Well, we have that the 0th term is equal to 0 and the first term is equal to 1. So what we can do is we can create a system of equations. One equation in the system will be when we plug in 0 for n. Another equation in the system will be when we plug in 1 for n. So that's what we're going to do. We're going to make a system of equations. And the first one is when f sub 0 is equal to 0, which is also equal to whatever happens when we plug in 0 for n. So we get c1 times phi to the 0th power plus c2 times 1 minus phi to the 0th power. And then f sub 1, the first term in the sequence, is equal to 1, but it's also equal to c1 times phi to the first power plus c2 times 1 minus phi to the first power. Now, if we simplify these equations just a little bit, well, we get this. The 0 is equal to, well, anything to the 0 power, well, that's not 0. Anything else to the 0 power will just become 0. So C1 times phi to the 0 power, well, phi to the 0 power is just 1. So we get C1 plus C2 times 1 minus phi to the 0 power is still just 1. And then in our second equation, if we take something to the first power, we don't even have to have the exponent there. So we get 1 equals C1 times phi plus C2 times 1 minus phi. So now our task is to solve this system for C1 and C2. We're going to use substitution. That's the easiest way to do this. First, I'm going to solve this first equation here for C1. So this actually will get us that C1 is equal to negative C2. All I'm doing is I'm subtracting C2 on both sides of this first equation. Now I'm going to take this second equation over here, and I'm going to plug in negative C2 for C1, because we know that C1 is equal to negative C2. So I'll get 1 equals negative C2 times phi plus C2 times 1 minus phi. Okay, so now I can solve this equation for C2. We can factor out a C2 on the left side, and we get 1 equals C2 times negative phi plus, and then we factor out here, plus 1 minus phi. And then inside this parentheses over here, we get 1 equals C2 times 1 minus 2 phi. All we have to do is just combine like terms and act like phi is a variable, even though it's a number. And then we can divide both sides by 1 minus 2 phi. So what we get is that C2 is equal to 1 over 1 minus 2 phi. Now, what was phi in the first place? Phi is the golden ratio, which is 1 plus square root of 5 over 2. So it's 1 over 1 minus 2 times 1 plus the square root of 5 over 2. Okay, now these 2's over here cancel. So we're left with 1 over 1 minus 1 plus square root of 5. So now if we distribute this negative, we get 1 over 1 minus 1 minus square root of 5. 1 minus 1 is, of course, 0, so we're just left with negative square root of 5 on the bottom. So our final answer for C2 is negative 1 over square root of 5. We're not going to worry about rationalizing the denominator. It's okay. I know your 8th grade teacher was probably like, you have to rationalize your denominators. Don't worry about it. It's okay. It's okay. It's going to be okay. So we know that C2 is negative 1 over square root of 5. C1 is going to be negative C2. And then C1 is negative of negative 1 over square root of 5, which is just 1 over square root of 5. So remember, our explicit formula was C1 times phi to the n plus C2 times quantity 1 minus phi to the nth power. But we figured out what C1 and C2 are. We got that C1 was actually positive 1 over square root of 5 times phi to the n plus, and then we got C2 was actually negative 1 over square root of 5, negative 1 over square root of 5 times 1 minus phi to the n. Now, if we factor out 1 over square root of 5, this, my lovely, wonderful friends, is Binet's formula. We did it. This is Binet's formula. Now, believe it or not, whatever you put in for n, you will get out a term of the sequence. You will get out an integer, in fact. This blows my mind every time, because what have we got here? We've got an irrational number, we've got an irrational number over here, and we got an irrational number over here, but somehow, when we take all this irrational stuff and we multiply and subtract and all this kind of stuff, we get an integer. Let me show you. So I should have put at the top of the screen when I edited this all the Fibonacci numbers up to the 12th one. We're going to use that to test out if this works on the Desmos Scientific Calculator. Now, Desmos is not sponsoring me. I love Desmos. Desmos is great. It would be really great if y'all sponsor me because I really need some money for grad schools, if you know what I mean. So what I'm going to do is I'm going to type in Binet's formula into here. 1 over square root of 5 times the golden ratio. We're going to actually have to write out what that is. The golden ratio phi is 1 plus the square root of 5 over 2. We take that to the nth power minus 1 minus the square root of 5 over 2, which we know is the same as 1 minus phi to the nth power. So we're getting this warning sign because we have not told Desmos what n is yet. Once we tell Desmos what n is, it's going to be able to calculate this. So let's go to a new line and we'll say n equals. Now let's just test out the first few terms of the sequence. So now when I put in 0, I should get out the 0th term of the Fibonacci sequence, which we said was 0. I put in 0. What do you know, folks? I get 0. I put in 1. I should get 1 because that's the first term. What do you know? I get 1. When I put in 2, the second term of the sequence is 1. So I should get 1. And I do. When I put in 3, I should get 2. And I do get 2. When I put in 4, I should get 3. We get 3. When I put in 5, I should get 5, just like that. When I put in 6, I should get 8. And I do get 8. When I put in 7, I should put in 13. The 12th term, I should get 144. Watch this. I get 144. This works. This formula works. So now we can use this to figure out what really, really late terms are in the sequence. So if I want to figure out the 100th term, all I have to do is just plug in 100 into this formula. And it's this giant number, 3.542 whatever, times 10 to the 20th power. It's ridiculously giant, right? And now imagine what would happen if you had to figure out all 99 of the terms before the 100th term, which all are also probably equally giant numbers. And then you add those all up together, and then you add up the 100th term. I mean, it would just take forever. This is way faster. You just plug in 100 in this formula, and you get the 100th term in the sequence, which is a ridiculously giant number. It just makes our lives easier. So anyway, that's Binet's formula. That's the vibe. Thank you so much for watching. I'm so glad that you're here. Please like and comment and subscribe. Tell your friends and ring that bell so that you can get notified if I make any new math videos. Tell me what kind of math videos you want to see, and I'll see you next time. Thank you so much. Bye!